who has joined us today for the webinar. We'll go ahead and get started, but a few notes first. Audio will be muted for all attendees during the webinar, but you can ask questions at any time at the bottom. We will save those for the end and do a question and answer section after the end of the presentation. We will be sending out an email with a recording of this presentation. That usually typically comes out within 2 to 3 business days, the email you registered for this webinar with. You can also chat with us at the bottom of your screen if you have any technical difficulties. This presentation is also available for CEU PDH credits in the states of Idaho and Utah for electricians and engineers. I'll send out my email as well in the chat so you can reach out to me for details about that. Other than that, we'll go ahead and turn it over to Craig for today's presentation.
All right, thank you, Tyler. We've done 2 webinars on medium voltage drives thus far. One of them was comparing medium voltage drives to low voltage drives. And I think that's a really good one if you have never used medium voltage drives, because they are really quite different than low voltage drives. The other one was on the top 10 things that you should look for when purchasing a medium voltage drive. This time we're going to get into medium voltage drive history, and we're going to talk a little bit about variable frequency drive fundamentals. Now, we're not going to redo all the things we did in our basic VFD class. We're just going to talk about a few things that are going to be important in order to help us understand where VFDs are today. And so we're going to start by showing you the torque speed and current speed curve of an induction motor. Now, the induction motor, when you start it, meaning that you close a contactor and all of a sudden you apply 60 hertz to that motor, but the rotor hasn't started turning yet. We would call that locked rotor, and that's over here on the left. And you're going to get approximately 600% current, let's say 6 to 7 times current. On this particular graph, it shows about 650%. And then as the motor comes up to speed, then you can see that the current continually comes down until when it gets very close to full load speed. Actually, between about 100 and between 50 and 150%, the current's pretty much proportional to the torque. Now, it is separated from the torque a little bit. I think primarily in this case, just so that the 2 graphs don't run over each other, so it makes a better looking graph. But basically, current and torque are about proportional in that 50 to 150% range, where 50% torque is 50% current, 100% torque is 100% current, and so forth. The blue line is your torque curve. Your torque generally starts higher than 100%, but could be kind of all over the map depending upon what that torque is. In many motors, the torque will actually dip a little bit. That's not shown on this particular graph. And the lowest point then is called the pull-up torque, and then it gradually increases until this high point is your breakdown torque, and then it comes down. And so we're generally running in the 100% and below, or we'll say 150% and below range. So we're running in this linear portion. And all of the rest of the curve is what we would call the starting portion of that drive. So here's another one that just shows the torque. There's your locked rotor torque. Locked rotor meaning that the rotor has not started turning yet. Pull-up torque is your minimum torque, wherever that happens to be. Then you have your breakdown torque, and then you get into here. Now, notice that with a variable frequency drive, you never start a motor, you only run a motor. What does that mean? Well, you see the shaded portion here on this blue graph. You're only in that shaded portion. You never get in the other portions. And the reason for that is, think about an elevator. You know, this is a kind of a common example, is when you're in an elevator, aside from the vibration in the elevator, you have no idea how fast you're going. You know how fast you're going in comparison to the walls of the elevator, and if you were to jump, but you have no idea how fast you're going in relation to the building outside the elevator. It's the same thing with a motor. That rotor inside knows how fast it's going in comparison to the magnetic field going around that stator. And the magnetic field going around the stator, let's say in an 1800 RPM motor, is going 1800 RPM. And so it only knows the difference between its speed and that 1800 RPM going around the stator. So in an adjustable frequency drive, we never get into the starting portions of that motor curve, only the running portions. And we start out way down here on this red curve. And so let's say we'll say we're running at 4 hertz. We're not starting at 4 hertz, we're already running at 4 hertz. Therefore, guess what? Your current is proportional to the torque, and you get 50% current at 50% torque. Now, if we were to go back here, what do we get? We get, in this case, let's say 175% torque at 600% current. So one of the figures of merit is for running a motor would be torque per amp. Well, obviously my torque per amp is not very good in the starting portion of the curve, whereas my torque per amp here is very good. It's basically 1-to-1, 1% torque for 1% current. And then as we increase in speed, we simply increase the frequency, and this whole torque speed curve goes to the right and to the left, depending upon what frequency we're running. And the drive makes sure that we never allow this to get into the starting portion. So we will never see 150% current on a VFD. In fact, in most loads like fans and pumps, we may never see more than 100% current, whereas when we start them across the line, we're seeing 600, 700% current. Let me mention one more thing. What is the current into the motor versus the current into the drive? Well, as I told you, on a variable frequency drive, the current into the motor is proportional to the torque. So let's assume we have 100% torque, but we're only running at 10% speed. Well, if that's the case, then we have 100% current because we have 100% torque, but we only have 10% voltage because we're running at 10% speed. That's out of the drive, from the drive to the motor. What about the current into the drive? Well, the voltage into the drive is always from the line, right? It's 100%. And therefore, our current is only 10%. So out of the drive, we have 10% voltage and 100% current. Into the drive, we have 100% voltage and 10% current. It kind of acts like a transformer there. And so that's kind of amazing to think that you can get 100% torque and 100% current into the motor with only 10% current going into the drive. If you started across the line, you would have, like we said, 600 to 700% current going into the drive. And that whole thing ramps up nice and smooth. So it's great for standby generators because it allows the generator voltage regulator just to follow it up. Let's talk about controls a little bit. I come from the age of DC motors. You know, in the AC motors, AC drives were, in my opinion, kind of introduced in 1987, 1988. Now that's kind of a lie because they already existed by that time and had existed for some time. But that's when the IGBT was invented, and that's when drives really took off and became very reliable and very cost effective. DC drives, on the other hand, have been around for a long time, and I will show you the dates in a few minutes when we get into our time graph. But I was the director of engineering for a steel mill. Most of the drives in our steel mill were DC. And so with a DC motor, you can see you have a field here, and we're going to talk only about shunt wound here because I'm already getting into the weeds enough as it is. We won't get into series wound or compound wound or anything like that. But you basically put a certain amount of current into that field, and it creates a constant flux or a constant magnet. And then by controlling the voltage through the armature, you control the DC motor speed, and you can make that speed very exacting. DC motors many times had tachometers on them, and so you would connect a tachometer to the DC motor, and that would tell that DC drive exactly how fast the motor was going, and it could adjust the motor speed very precisely. But in addition to that, it could adjust the motor torque. There are many applications where you need to control the torque and you don't care so much what the speed is, you care what the torque is. For instance, on a winder, in the steel mill, we would make a big long strip of steel and then we'd have to wind it into a coil. So it would go onto the winder and we would make a big coil of wire. Well, the speed there wasn't really important and it would change depending upon the diameter of the coil. What was important was the torque because we wanted to control the tension. And so DC drives were very good at that. By contrast, AC drives were not very good at either of those things. They weren't that good at speed control, although you could put a tachometer on them and get a very precise speed. They couldn't control torque because they have nothing in them that allows them to sense what that torque is. Well, as you might know, things have changed. AC drives can now do basically anything that a DC drive can do, but it's just not easy. DC drives can directly sense the torque. AC drives can't. What you have to do is go through a matrix, and that matrix, you have to solve a matrix. You know how many calculations that takes. And so it takes a lot of microprocessor time in order to solve that matrix. And you have to do it very fast over and over and over and over again to determine how much of your current going into that motor goes towards magnetization of the motor, and how much current goes towards the torque of the motor. So if you do this, we call this vector control. So typically we recommend scalar control or volts per hertz control. And when you're operating a pump versus a pump or a fan or something like that, I still recommend using scalar or volts per hertz control because it's very easy, it's very stable, and it's not likely to give you problems. On the other hand, if you want to have precise control, you probably want to go to vector control. And if you actually want to control the torque, then you have to go to vector control because scalar control just doesn't work. Now, in order to do vector control, you have to have two things. Number one, you have to have a very expensive, very high-speed microprocessor. And second, you have to have a tachometer or an encoder. And a lot of people, they don't want to put a tachometer or an encoder on their drive, and they don't want to spend the money. And so vector control has been expensive and not used a lot. Well, again, things have changed. So these days, number one, microprocessors that we now call digital signal processors, because they're made for variable frequency drives and do a lot of these calculations in hardware and are very fast, are also very cost effective. And so what used to be expensive is now fairly inexpensive. Secondly, we have something called sensorless vector. Now, sensorless vector is not quite as good as having an encoder on there, but sensorless vector allows you to use full vector control without the encoder. And it's frankly really, really good. And we have applied in many cases loads that either had a DC drive with an encoder or loads that had a very expensive AC drive with an encoder. And they've taken the encoder out and used sensorless vector, and that has worked just fine. So we live in a nice age. Now, the caveat here that I will tell you is that you have to tune the motor to the drive in vector control. And that's my big concern. Now, if you've got a low voltage drive, generally tuning the motor is pretty easy. You just uncouple the load, and so you have the shaft just spinning there, and then you say to the drive, tune yourself. And the motor goes back and forth and up to speed in the forward direction and up to speed in the reverse direction. And in 30 seconds or so, it stops and it says motor tuned. And that's it. I mean, it's very, very sophisticated, very, very complicated, but you don't need to know anything about it because it all is done by the drive. Medium voltage drives are the same, except that we tend to take a little more care with medium voltage, and we will tune them at different load conditions. But it's the same idea. Coming out of the drive, this is what all low voltage drives look like. We control the speed with the frequency, and the frequency is controlled by when these pulses go positive and when they go negative. All drives put out pulses. There is no drive that puts out a sine wave. Now you can put on a sine wave filter to help convert that output to a sine wave, but the actual waveform coming out of drive is this series of pulses. So we control the motor speed and the motor frequency by the frequency, and then the voltage. Remember, on an AC drive, we have to control the voltage along with the frequency. And if you're at 50% frequency, you have to be at 50% voltage and so forth. We control the voltage by the width, controlling the width of the pulses. So the lower the voltage is, the narrower those pulses are going to be. And that means that the peaks of them are still the same, but the pulses are going to be thinner, and therefore the average voltage is going to be less. Now, this is how pretty much, with the exception of maybe one drive I can think of, or a couple of them, like cycloconverters and so on, this is how all drives are built. We have a converter that converts AC to DC. We have a DC bus, and then we have an inverter that converts the DC to AC. The converter can use either diodes, not IGBTs, but SCRs, or IGBTs. We'll talk about that soon. Then we have some kind of energy storage mechanism. So basically, the motor runs off the DC bus. It doesn't run off the output, or off the input, excuse me. It runs off the DC bus. So we have to have some energy storage there. And then this converter basically just keeps the DC bus charged. We can store that energy in two ways, either in an inductor or in a capacitor. If it's an inductor, the inductors try to keep current constant, and so we call that a current source inverter. If it's a capacitor, then capacitors tend to keep the voltage constant, and so we call that a voltage source inverter. We'll talk a little bit more about current source inverters, but they are mostly a feature of history. Not many people use them anymore. Okay, so there's our current source, and there's our voltage source. Now, this is probably my favorite slide, and because I remember a lot of this stuff. I do not remember the invention of the diode, although I was alive at the time. Diode was the first solid-state device that could rectify, meaning if you had voltage in one way across the diode, it would allow current to flow. If you had voltage in the other direction across the diode, it would block that current. So I think of a diode as a check valve. It's very simple. It allows current to flow in one direction and one direction only. And with the solid-state diode, we were able to build rectifiers that could convert AC to DC, and that was very helpful in many locations where we needed DC. The next thing came along in 1961. GE developed something called the silicon-controlled rectifier. The silicon-controlled rectifier was a diode with a latch, or a check valve with a latch. So basically, you could not push current backwards through an SCR, but if you tried to push current forwards through the SCR, it would not let that current flow until you opened the latch or the gate. And so you could control that. And if you waited, let's say, you look at your positive sine wave, if you waited halfway through that positive sine wave before you opened the latch or opened the gate and allowed current to flow, you would actually get the equivalent of half voltage. This is the type of technology used in light dimmers when you turn on your switch, is they simply determine how much of that waveform they're going to let through. These things were fantastic, and this was the start of solid-state DC drives. Well, it wasn't long after that that Westinghouse came along and developed their own version of the SCR. And since GE had called theirs an SCR, Westinghouse called theirs a thyristor. So in the early days, if you bought a silicon-controlled rectifier, that was a GE device. If you bought a thyristor, that was a Westinghouse device. But they were both the same thing, essentially. Over the years, we have changed our terminology. So that original device invented by the General Electric Company is still called the SCR, the silicon-controlled rectifier. A thyristor has come to be any bistable device in the rectifier family, if you will, that can turn on but cannot turn off. You see, you can't turn a diode off, you can't turn an SCR off. You have to cause current to go backwards through those devices in order to turn them off. Think of a check valve. If you have a little latch on a check valve, once you open that latch, you can never close it again. But once the current flows backwards, then it will cause that gate to close, and then you're ready to go again, and the latch will be latched. So any of those types of devices now tend to be referred to as thyristors. So silicon controlled rectifier is a very specific term. Thyristor is a general family kind of term. Then we developed the bipolar transistor. Now, transistors were wonderful devices. And I can remember when I bought my first radio from Japan, transistor radio. I mean, it had no tubes in it. It was amazing. And it had 12 transistors in it. And these things can turn themselves off. Not only can they turn themselves off, but they can turn themselves halfway on or 3/4 of the way on. Unlike a thyristor, a transistor actually has the ability to turn itself on and off. And so you can see a transistor is a much better device than a thyristor. So on the top of this time graph, you're going to see that we are going to be talking about transistors. On the bottom graph, we will be talking about thyristors. And the difference is transistors can turn themselves off. Thyristors, you have to cause the current to go backwards through them in order to turn them off. And so the next device to be created was the gate turn-off thyristor. Now, this was the first device that we could actually turn off, but it was still a thyristor because it took a lot of current to turn it off. And I will show you that in a minute. You'll be kind of shocked. So we still call it a thyristor because the basic device can't turn itself off, but by putting a very large amount of current through the gate, we can manage to get that thing off. But it's still not what you would call a transistor. And the only reason we ever used a gate turn-off thyristor was that we didn't have a transistor in the required voltage and current ranges. The bipolar power transistors were still only available in very low voltages and very low currents. Well, along came 1987, and most of these drives were introduced in 1988. We invented the low voltage insulated gate bipolar transistor. That's the IGBT. And that was the cat's meow. Not only could you turn it on, but you could turn it off, and it was available in higher voltages and currents. And this device now, you cannot turn it on halfway. You couldn't use this device in your transistor radio because it's either going to be on or off. It only has two states, on or off. But it was fantastic, and that basically made all the other devices in the previous adjustable frequency drives obsolete. And this is when we had the very first fully digital IGBT-based drives, and I was involved in doing UL testing on some of these and introducing them to the US, and they were really amazing. It's also amazing to me that if you look at a drive in 2020, it's basically the same as those drives that were built in 1988. The microprocessor has changed significantly, but the topology is the same. We still use the same devices, the same IGBTs, and so on. So the Japanese did a very good job, basically Mitsubishi, Toshiba, Fuji, and that's where all modern technology in these drives started. Well, unfortunately, IGBTs still had some limitations in terms of their voltage and their currents. And so when you wanted to get into very large drives, then we had to go back to the thyristor family. And they came up with a new device called an integrated gate commutated thyristor. And basically it has all the drawbacks of a thyristor, but it is available in much higher voltages and currents. And we did that because there was no such thing as a medium voltage IGBT. Man, would it be nice if we could get an IGBT that was medium voltage. Well, I don't know whether that was ever going to happen. but it did happen. And you can see in 1997, 98, something like that, the medium voltage insulated gate bipolar transistor came out. And now we were able to use this IGBT in much higher voltages. And for the most part, that obsoleted all the other devices that we were using in the thyristor family. Not completely, because still, when the medium voltage IGBT came out, it still had voltage and current limitations. And so we continued to use thyristors, and some of these really new thyristors actually were very, very good. But we certainly would rather be in the transistor family than we are in the thyristor family. And so next came out as the symmetrical gate commutated thyristor, a little more advanced thyristor that was available in higher ratings. And finally, out came the injection enhanced gate transistor. You can think of this as just an IGBT on steroids, because it has all of the same operating conditions of an IGBT, but available to transmit huge amounts of power. So most drives, not all, but most drives have moved towards these IGBTs. And if you have a really large drive, you could actually get that IEGBT. We'll talk about that, or IEGT. What are the comparison areas? Well, the gate power to turn it on and off. The less power it takes to turn it on and off, the better the device. The switching speed, the faster the switching speed, the better the device. Continuous current ratings, obviously you need as much current as you need for the motor. Forward and reverse blocking voltage, of course, that is important if you're going to use this at higher voltage ratings. And then your physical mounting and your thermal characteristics. Take a look at a GCT and notice that the GCT looks like it switches on a little slower, but the main idea is it switching off. Notice how much time it takes to switch a GCT off as compared to an IGBT. The IGBT switches off about the same as an IEGT. And when you think about this, if you have a device like a transistor that's half on, that means that 50% of the voltage is going to be dropped across that transistor, and 50% of the voltage is going to go to the load. And therefore, you take 50% of the voltage times the current, and that represents the losses in that transistor. In other words, huge. So when the transistor's all the way off, you have very low loads, very low losses, excuse me. When it's all the way on, you have very high losses. I'm sorry, let me rephrase that. I misstated that. When it's all the way off, you have very low losses. And when it's all the way on, you have very low losses. The high losses come when you're switching it from off to on or on to off. And that's why the carrier frequency in most drives, we should try to keep that low, because if you say double the carrier frequency and you switch twice as often, you'll generate a lot more heat because your switching losses will be doubled. Now take a look here. To turn on and off that GCT takes 4,000 amps going into the gate. So that's a thyristor type device, and that 4,000 amps is not going to act as quickly as an IGBT, and you're going to have very high losses in it. So if we look at an IGBT, 1.5 amps, that's a huge difference. And you can see, because of the switching speed and because of the gate current, we really prefer to use a transistor-based device as opposed to a thyristor-based device. There's a GTO, a gate turn-off thyristor, and perhaps some pictures are fun to look at of these devices. There's a gate-controlled, again, thyristor, and the mounting of that, and you can see the ruler down there that gives you a little feel for the size. Here's some early GCT and gate driver boards. This one has 36 electrolytic caps in it and 21 field effect transistor switches, so complicated devices. Here again, a gate-controlled thyristor, and showing some of the operating characteristics of that. And here is the one we love, the IGBT. Now, if I look at this IGBT, I don't know whether that's medium voltage or low voltage. They tend to look similar. But you can see that's 4 inches by 4.5, and I know because they told me this particular transistor is 400 amps and 3,300 volts. So wonderful, wonderful devices that we now have available to use in our medium voltage drive. The IUGT is the latest generation, only one manufacturer makes it, and you can go up to 4,500 volts and 4,000 amps. Now take a look at this. That's 3,300 volts, but 400 amps. This is 4,000 amps. And here's a picture of it. Amazing device. You can see the calculator there. Amazingly small device to produce 4,500 volts and 4,000 amps. But they're a little pricey, and you're not going to find IUGT in your 1,000 horsepower drive. You got to get into some very large drives before you can afford to use that device, because let's face it, 4,000 amps is a lot of current, and that's a lot of power in medium voltage. So there's the gate circuit summary. We talked about our power device losses. This is a graph that's great, so you can see when we turn the device on, we have huge losses. And then while the device is on, then we have only our conduction losses, much, much lower than the losses turning on and turning off. And then finally, we have our turn off losses. And so you want to turn it off quickly, and you want to switch as little as possible. Here's some of your power switch ratings. We recommend above 3,300 volts, you use a sine wave filter, and we will talk about why that is in just a moment. So let's talk about some drive topologies. The drive topologies in low voltage drives are mostly the same. In medium voltage drives, we have a number to choose from. So here's a load commutated inverter. Won't get into this too much, but that was your first adjustable frequency medium voltage motor. And you see over here it says SM on the motor. That's synchronous motor. You had to use these with synchronous motors. And because our devices were limited in voltage, we put several devices in series. These were not as reliable as we would have liked, but they were pretty good. And the fact is, Westinghouse, which I worked for at the time, and GE were making these very commonly. They were expensive, but they worked, and we still have load commutated inverters working today. Here's some alternate LCI configurations in different pulse configurations, and we will talk about pulses in a minute. Now, current source devices were popular in the 1980 to 1995 period because you didn't really have a lot of other choice. We simply didn't have devices that could turn on and off, and so by using current source, we were able to make drives. Pretty much every manufacturer's gotten rid of their current source drives. I think there's probably only one manufacturer that's still making them, and even that manufacturer has recently offered a voltage source inverter. I see no reason to buy a current source inverter these days, but they used this big DC link inductor. They were fairly low response rate because you couldn't change the current in that DC inductor very quickly. They had very poor input power factor, slow transient response. You could get resonances, and so there were voltage source inverters were much better, but this is what we had at the time. Here's current source inverter, and we always recommend an isolation transformer on a current source inverter. We recommend an isolation transformer actually on all medium voltage drives. Some people have a direct to drive solution, and that can cause some really high voltages that can cause breakdown of insulation in your motor. Here's a diode rectifier, and here's an active rectifier, which we're going to talk about some more in a minute. All right, here's our pulse width modulated waveform, and I want to talk a little bit more about that. What you see there is the way all low voltage drives are built. And the reason for that is you can't afford to do more because they would be way too expensive. So in that case, low voltage drives has 6 IGBTs on the output, and you can either turn it on or off. If you turn that IGBT on, it goes positive. If you turn this IGBT on, this line goes negative. And so you're either positive or you're negative, And of course, you can have a 0 voltage in there if both are off or both are on. So you're basically going from 0 to the peak very, very quickly. And that's what causes a lot of high voltages and breakdown of insulation in low voltage motors. So you know that in a low voltage motor, we like to have a VFD rated motor, and that means it has premium insulation in it, rated about 1600 volts as opposed to 1000 volts. And that's because of these peak voltages. They can cause transient voltages double that size, and so you get some very high voltages in there, and it's hard on motor insulation. Now, this is a low voltage IGBT based inverter built by T-Mike in Japan. Robicon popularized this in the United States. By the way, if you've been in any of our medium voltage drives before, I talked about T-Mike. It's probably the best kept secret in medium voltage drives. This is Toshiba, Mitsubishi, and GE. All three companies put all their products together in order to create one super company, if you will. And so when you see T-Mike, that has all of the products of Toshiba, Mitsubishi, and GE. And so they have a very large product line, and they make pretty state-of-the-art drives. We'll show you some of their products. This particular one, some people call this the Robicon technology. It was also in use by T-Mike when Robicon introduced it. But they put cells in series. So these are actually little mini inverters. They actually have a DC converter, a DC bus, and an output inverter, but then they put it in series. And so these are low voltage cells, but by putting them in series, they can get medium voltage. So this is kind of a nice technology. And in doing this, they can get stair-step outputs, which we're going to talk about. One of the real disadvantages of this is that the energy in each of those is in electrolytic caps. Pretty much all low voltage drive use electrolytic caps, but electrolytic caps, they dry out. If you leave the drive de-energized for some time and then you energize it, they can explode. And I know from having bought, I'll say Robicon because they're out of business, so I don't like to criticize anyone, but since they're out of business, I can probably talk about it. I had 13 of these drives when I was at the steel plant, and when they ran really, really well. I mean, they were astonishingly good. I was very happy with them, but because of those electrolytic caps, we got to where we never wanted to de-energize the drive because seemed like, and I'm exaggerating here, but it seemed like every time we turned it on that one of those big electrolytic caps would blow up. And in a medium voltage drive, you're looking at maybe $10,000 per cell to go in and replace one of those cells. So that was a kind of a drawback. These things have been improved since. They are much better. Robicon was bought by Siemens. Siemens is making these. T-Mike is making these. And a number of other manufacturers have now begun to make them. They are not regenerative. They have a larger parts count, larger footprint, and we would really like to get rid of those electrolytic capacitors, which we have done in some of the modern drives. Now, what's nice about this? Well, you don't have to turn it on and off. There is no such thing really as a medium voltage variable frequency motor or a VFD rated motor. You kind of are more sophisticated and you look at the motor and you look at the drive. But this is fantastic because in this case, we're looking at what, 25 level. Boy, that's a lot. I'll show you levels in a minute, but notice how we switch on one of these devices here and we just get a little bit of voltage. Then we switch on another one and then another one and then another one. And so we're actually creating a sine wave by using the stair-step technology. And quite frankly, this is almost as good as a sine wave. I mean, I would say it's as good as a sine wave, which is what we would really like. And you get rid of the problems with your motor voltage insulation because you're only applying voltage in very, very small steps. So it's very easy on your voltage. And you can just take a standard medium voltage motor, put on something that has these multiple steps on it, and it'll do just fine. This is some drives that have been in the field. The 2.3 kV or the 3 kV only used 3 devices in series and gave you 7 levels. 6.6 kV and the 4160 had 5 of these. The 6.6 had 6, and that gives you 13 levels. And if you want to go to higher voltages, you just put more devices in series. Some manufacturers are offering redundant, and I liked that. I thought that was really cool because you have a redundant cell, and if any cell in here fails, then they put a bypass SCR in there, so they bypass that cell, and then you have a redundant cell. The problem for me is I did this in all of my drives, and it never actually worked. Every time we had a cell failure, we blew up the drive, and it stopped, and we had to repair it. So I'm not convinced that this actually works. It always works in the lab, but in my experience, it never worked in the field. So I would rather not have the N+1 and have less devices and less parts counts because there's less to fail there. This is called neutral point clamping. I won't spend much time on this because we are getting close to the end of our time here. But let me point out that this is only available with medium voltage drives to the extent that you can add more devices, which you can't afford to do in low voltage drives. You can have positive, you can have negative, or you can clamp it at 0 volts. And by clamping, it keeps that star point or the neutral point in the motor at 0 volts. And it's a great technology. It's available in a number of manufacturers' drives. Now here's our 2-level inverter. This is the way all low voltage drives are created. And as you'll notice, we go from 0 voltage to peak voltage very quickly, as fast as that IGBT can switch, because we want to switch quickly in order to limit our losses. But the faster we switch, the higher the voltages tend to go, and we can get peak voltages and reflected voltages up to double, and that can break down motor insulation. So going to a 3-level inverter is a huge advantage. And you can see in this waveform, there's 0 is 1 level, then we've got a 2nd level there, which is half voltage, and a 3rd level here, which is full voltage. So now we're only switching on half the voltage at a time, and that is much better on motor insulation. But even half voltage, if we double that half voltage, which can happen in a transient, plus the other half, we're still hitting that motor potentially with 150% voltage, and that's kind of tough. So we would never recommend using a 3-level inverter over 2300 volts. Now, I know there's at least one manufacturer that I saw recently, a very big name manufacturer, that's selling a 3-level inverter at 4160 volts. I think that's a bad idea. I'm not going to mention who that is, but we would say don't use a 3-level inverter over 2300 volts unless you put a sine wave filter on the output. It just creates the spikes too high. And even that manufacturer is saying you have to be very careful with wired lead length and so on, and you may need an output filter. So the next step up is a 5-level inverter. Now this was the cat's meow at the time. And with a 5-level inverter, of course, 0 is one of your levels. And so you're switching on only a quarter of your voltage at a time. And that's fantastic. And so this is perfect for a 4160 or 6600 volt inverter. And I would say for 2300 volts, I'm okay with the 3-level. Anything higher than that, 5-level would be an absolute minimum for me. Here is a 3-level circuit neutral point clamped. Here's an IGCT inverter that is a 3-level, an older design. Here's an IEGT that has a 3-level output. And I'm going to move through some of these because we're getting to the end of our time. Now, this is a medium voltage IGBT. That is that 5-level inverter. This is still available. It's a little bit of an older design, but it's a very, very good inverter. Lots of them out there. And you can see here's the transformers, and here's your inverter section. And at 5 levels, I would pretty much be happy using this on anything. And that is your 5-level inverter. Now, let me see if I can find a place, I'm going to come back to that. I apologize. Yeah, let's look right here. Let's talk about pulses for a minute. In general, and this is not completely true, but in general, if you have one transformer secondary, that would be a 6-pulse drive. If you have 2 transformer secondaries, that would be a 12-pulse drive. 3 would be 18 pulse, 4 would be 24 pulse, and so on. And the higher your pulses, the lower your harmonics. So we're not going to get into harmonics too much here because we did a whole section on harmonics. But if you have a multi-pulse type of drive, generally the number of transformer secondaries multiplied by 6 will give you your pulses. In medium voltage, never use a 6-pulse drive. They have horrible harmonics, and most low voltage drives are 6-pulse. 12-pulse drive is much better. You can get down to maybe 12% or so harmonics. An 18% will many times get you under 5%, and a 24-pulse will definitely get you under 5%. Once you go above 24 pulse, you're probably not getting anything for your money. It sounds good, but the performance won't really be much improved. So my opinion, if you're going to use a multi-pulse technology, always insist on at least 24 pulses. Now here's the MVE2. This is kind of, I would call it the latest and greatest in drive design. If you look down here, it does have 3 transformer secondaries, but this is not a multi-pulse drive. This is an active front-end drive, and so it's kind of different. And with that active front-end drive, you have a 20-year mean time between failure. That's just unheard of. You can get, or not you can get, but it has standard regeneration. So you can do regenerative braking. You can put it on a conveyor and take that power from the conveyor, put it back on the line. Notice at 4160 volts, this has 9 levels. So I suggested 5 was really good, and I'm happy with 5. But let's face it, 9 is better than 5, right? And here's a waveform. If you go to higher voltages, you get even more levels. These do not have electrolytic capacitors. They have film-type capacitors, so you get away from all the problems there. And it's 100% power factor and 2% total harmonic distortion. Now, a typical multi-pulse drive will have about 97% power factor and under 5% total harmonic current distortion. And that's still really, really good, but not as good as this. I mean, this is state-of-the-art in drives, 100% power factor at all times. And in fact, if you want it to, if you're not using full load current in the drive, this can actually correct your power factor in the plant by actually generating leading bars. It won't do that unless you ask it to. If you don't ask it to, it has 100% power factor. But that's a fantastic drive. Here's what it looks like. Very simple. You've got your isolation transformer, and then however many cells you have for the particular drive. We're about done here. This is a 5-level IEGT. I wanted to have a picture of an IEGT drive because that's that little device that I'm really amazed at. The 4,000 amp semiconductor. And a single unit here is 20 MVA. That'll be a little over 20,000 horsepower. And your maximum capacity is 80 MVA. You get that by paralleling 4 of the 20 MVA devices. And you can see this has got multiple transformer windings, so you would expect that to be a multi-pulse drive. What is evolving in drives now? We're getting larger and larger motors. People now are trusting larger and larger motors to drives because they're so reliable. And you can get, like in natural gas compressors, not uncommon to see 80,000 horsepower motors. And so we're seeing more and more very, very large drives. Environmental factors, sometimes they have a hard time with getting EPA approval. And so instead of putting combustion turbines in, they will substitute very large electric drives that's driven by the EPA. And you can get very large drives. I've shown some in here. This is a 5-level IGBT. You get 8 MVA. Think of an MVA as 1,000 horsepower. That's, approximately right. Here's that 5-level IEGT that I talked to you about that comes in 20 MVA models. And here's a 5-level IEGT inverter that comes in 30 MVA. And so by paralleling 4 of them, you could get 120 MVA, and that would give you better than 120,000 horsepower. We do have a sale on these drives here, the 120,000 horsepower drives. We have a buy one, get one free, but you have to buy today. Okay, maybe only I think that's funny. So here's some parallel connections, and you can see kind of how these drives are paralleled. And there is a kind of a layout showing how to parallel drives. So that's pretty much it. I know I got in the weeds there, but we've covered a lot of other stuff with medium voltage drives in our other webinars. And all those webinars are available for you to view. And so if you want something that gets less in the weeds and more basic and starts from the standpoint of you not knowing a lot about drives, then you can watch one of those. But I think this is very interesting. It gives you a little bit more in-depth discussion of vector control drives and of the evolution of medium voltage drives and the different types of technologies that are on the market. So I'm done. I will turn the time back to Tyler.
Great, Craig. Looks like we have a couple questions so far. Feel free to continue submitting questions. The first one's actually a two-part question. It says, as a municipality, how would you go about specifying a medium voltage drive for future projects? And how does the specification change based on application?
Okay, that's really great. So, you know what you want to do, and by the way, let me mention this: if you wanted to go back and watch our webinar on the top 10 things to specify when specifying a medium voltage drive, then that's great, because that whole webinar basically was an answer to this question. But let me mention this. Here's the things that I think are important kind of in a nutshell. Number one, reliability. I would like to know what the field proven reliability is of that VFD. Now, I understand that when you get into reliability and manufacturers calculate their mean time between failure, that can become a liar's contest. So I do have to kind of take that with a grain of salt. But the other thing is take a look at where those manufacturers are putting their drives. In the steel mill area, as I said, you know, that's near and dear to my heart because I was the director of engineering for a steel mill. You can't afford to go down. You cannot afford to go down. It's $100,000 an hour that we lose whenever we go down at Geneva Steel. So if at Geneva Steel, we couldn't go with a manufacturer where if a drive failed, they would say, yeah, our tech is busy for the next 2 weeks, but we can schedule you on April 6th. No, that doesn't work. We want a manufacturer that is very active in the steel mill market, that has extremely good reliability, field-proven reliability, and that can have 3 people on a plane within a couple of hours. So look for a manufacturer like that. Look for a manufacturer that has lots of installations in steel mills if you want your top reliability. Next, I would look at harmonics. I would specify at a minimum that all medium voltage drives should have less than 5% total harmonic current distortion. Next, I would look at the number of output steps in the waveform. I would specify a minimum of 5 steps in the output voltage. And then I would kind of look at the drive. Those are kind of the main things that I am concerned about. But then you want to look at how it's built, what's the reputation of the manufacturer, how long have they been in the drives business, and probably the most important thing of all is field service. Now, I'll brag here a little bit. You'll notice I'm not really promoting our product that much. I'm trying to keep this technical, but a lot of people have bought drives from major manufacturers, and when they go around to trying to get service for that drive, the service guy is 2 or 3 weeks out. Well, that isn't going to cut it for a medium voltage drive. So I would want to know how many service people there are in the United States. And I don't want some guy who works on low voltage drives all the time but went to a medium voltage drive school. I want people who work only on medium voltage drives, because only there they're going to have the experience to really get in there and take care of business. So if you say how many people can work on your medium voltage drives, they're going to take all their drives guys that work on low voltage and tell you that's what they've got. I want to know how many people work exclusively on medium voltage drives. And then, of course, I want to know how many people are in my town or close to my town. How long is it going to take them to get there? In our case, we have 3 people in Salt Lake that are qualified to work on medium voltage and basically are medium voltage people. And then T-Mike backs it up with about 100 service engineers nationwide in various locations. So if you can't get it repaired, then the best drive in the world is not going to work. So that's kind of my in the nutshell. And again, watch our 10 things to look at when specifying a medium voltage drive if you want a little more detail and want us to go through and talk about that a little bit more.
Next question is, what is the effect of harmonics on medium voltage drives, and how do you remove harmonics in medium voltage drives?
Okay, the really nice thing is low voltage drives. You know, we had a whole webinar on low voltage drives. Low voltage drives make a lot of harmonics. And so how to get rid of those harmonics and so on is a big deal. And it took us a long time to discuss that issue. The good thing about medium voltage drives is some of the technologies I've talked about, like the multi-pulse drives with the various levels and the active front end drives. There is absolutely no reason not to buy a medium voltage drive that can give you less than 5% harmonics. And if that medium voltage drive has to have a filter on it, if they're saying, oh yeah, we've got a harmonics filter that we can put on this drive to give you less than 5%, stay away from that drive like the plague, because that says the drive itself is very dirty, has high harmonics, and they're having to put on a filter in order to filter those harmonics. There's no reason for that in 2020. These drive technologies, whether they be an active front end or a multi-pulse type of drive, can easily give you less than 5% harmonics without having a filter. They simply generate less than 5% harmonics. So that's a huge difference between medium voltage and low voltage. Medium voltage, it's easy. Just specify less than 5%. Low voltage, not easy at all. And in fact, there's really no technology in low voltage that can give you less than 5% at all of your speeds and loads. You can get close, but it's very difficult. So just specify less than 5%. And you will not pay a premium, and make sure I would put in my spec, no filters. This drive has to have less than 5% harmonics without filtering. And then on the output, we generally don't talk about that as harmonics, although in theory it is, but we generally look at levels. And again, as I've mentioned before, I would specify a minimum of a 5-level drive. If you can get like a 9-level drive, gee, that's even better.
Have there been any major changes in enclosure styles or footprint size in the last few years?
Yeah, great question. And the answer is yes. Now you can imagine with medium voltage drives, they're very expensive to design. And so they tend to have a long life. And so you can get drives that are still being sold that are really good state-of-the-art drives that were maybe designed 15 years ago. But one of the things that's getting more popular in drives is outdoor enclosures. That's still an issue because they need a lot of cooling, and a lot of people just put medium voltage drives in a Connex box or an e-house and put air conditioning on it. But we're seeing some drives actually built to come in outdoor enclosures. And I don't particularly like air conditioners because they tend to be not as reliable as the drive. But if you have an e-house and you have redundant air conditioners, there's nothing wrong with that. It's fine. But so we're seeing the outdoor enclosures. In terms of the footprints are getting smaller. They're definitely getting smaller. But I would be careful about that for two reasons. Number one, If you want to pack 10 pounds in a 5-pound sack, you're going to get a drive that's very hard to maintain. And secondly, if you want the thing to be an absolute lowest footprint possible, you may be sacrificing technology for that. For instance, you may find one drive has a smaller footprint than another, but the smaller footprint drive has a 3-level output to your motor, and the larger footprint drive has a 9-level output to your motor. Well, you really want to be careful about going with that smaller footprint, because you can be sacrificing performance. And so you want to be careful about that. Again, make sure you have at least a 5-level output, and 9 would be better. Or, of course, higher than that probably is not better than 9, because 9 is almost perfect. And you want to have less than 5% harmonics without a filter. But yet drives are getting smaller, and more importantly, they're getting less expensive. There are more manufacturers coming into the business, and the volumes are getting up there. And so that's causing drive prices to continuously decrease.
Back on the harmonics, we had someone ask, back on the low voltage side, how do you remove harmonics? They said that you had indicated that it's a daunting task to do that, so they're wondering what are some of those methods.
Yeah, it is a daunting task. And again, I would refer you to our harmonics webinar, because that will take you through all of the methods that we use. With medium voltage, the harmonics mitigation is built into the technology of the drive. With low voltage drives, typically harmonics has to be in addition to the drive. So you can do multi-pulse technology, for instance, by putting in 2 rectifiers and an isolation transformer with phase shifting. You can get 12 pulse. By putting in 3 rectifiers, and a transformer with 3 outputs, you can get 18 pulse. Now, an 18 pulse low voltage drive does not work as well as an 18 pulse medium voltage drive. You say, well, why would that be? It's because with low voltage drive, the 3 converters are in parallel, and so they don't necessarily balance very well. Whereas in medium voltage, those 3 converters will be in series, and in series, the same current has to go through all 3, and so they perfectly balance. An 18 pulse drive, a 12 pulse drive I wouldn't use. An 18 pulse drive I would, but they tend to be expensive, and there are other technologies that give you the same performance at better cost. A passive filter is the most common technology in the marketplace, and that's because it's at least half the cost of an 18 pulse and will give you the same performance as an 18 pulse. And that includes some reactors and capacitors that will filter those harmonics out. And then you have an active front end, and the active front end is really kind of the cat's meow, but it's also the most expensive. And then another technology is an active filter, so you can actually just put reactors on your drive, let it generate the harmonics, and then you can put an active filter on the bus and filter those harmonics out. And so you could have 10 drives and 1 filter to filter out the harmonics from all 10 drives. And that works well if the drives are small. So again, I would refer you to our harmonics seminar, because we spent a whole hour reviewing those and helping you to understand better than I was able to explain just now. In general, the best way to go is with a passive filter. They will increase your drive cost by about 30–35%, get you down to about 7–9% harmonics. They're very reliable. They give you transient surge protection. And in general, those are the most popular because you kind of get the most bang for your buck.
Great. It looks like that's all the questions we had today. So we'd like to thank everyone for joining us, and we look forward to seeing you next time.